again. This is John from Optics for Hire, and with me is Sergey Sidorovich. Hi, Sergey.
Hi, John.
Today, Sergey and I are going to talk about a project that he worked on related to an illuminator, a particular illuminator for IR illumination. This was a few years ago, and this was sort of concept development, I would say, was the stage of work that we were in. Sergey has been working on optical systems design for many years, and this is, I think, our 10th or 11th episode of Optical Engineers at Work. So I'm interested to hear Sergey to hear more about this project. So what were we trying to accomplish?
The client asked us to design an optical system based on the LED. This is infrared illumination, about 930 nanometers, and the aim is to create the rectangular field with good bright illumination and with a good
uniformity.
Yeah, with a high and illumination with a high uniformity. So, and one more additional task is choosing the angle and specifics of the illumination system in the way to satisfy some shadow placement from the object that is placed inside of this illumination field.
Okay, so we're doing probably some kind of motion tracking or something, and there's a shadow that there.
Probably, who knows?
Okay, so a couple of things I'm noticing here. This is your initial layout, and the first thing I notice here is that it's NSC, which that is non-sequential mode. Is that right? Can you explain why you use that for this product, this project?
The deal is in the potential light flares, reflections that can be seen in such systems. The LED is bright, and light flares and some reflections from the optical surfaces can be a source of the bright spots in the field. And in case if we are exploring and designing system that should provide high uniformity illumination field, in this case we use NSC mode for the simulation of the illumination field. But I need to admit that initially we create such lens system in the sequential mode of Zemax.
So you start with sequential mode and then later model in a non-sequential mode.
Yeah.
And non-sequential is what we typically use for illumination and systems rather than imaging systems. Is that fair comment?
Yes.
Yeah. The other thing I'm noticing is for LEDs, a lot of the times we would use a TIR lens for capturing the photons leaving the LED and projecting them onto the scene. You have a different kind of concept here, a condenser lens with two elements and then kind of an imaging lens. Why did you use this kind of architecture in this case?
Yeah, unfortunately, requirements for the size and placement of this illuminator requirements were too tight, and it is impossible to place TIR lens here in this design. And the most suitable way to make such a design was using the several lenses with some kind of apertures.
And so the TIR maybe would have too big of a diameter. Was that the problem?
Yeah.
So they just had kind of a narrow channel, because this is I would think longer than a TIR might be, but definitely narrower. Or maybe a TIR would be this length, but
it's difficult to say now. Yeah, but it's in the beginning of this project we reviewed possibility to place TIR lens here, and I remember that it was impossible for this project.
Because for TIR lens you generally need the smaller the beam angle, the smaller spot size, the larger the optic needs to be. So I don't know if that was a factor. So here is your system, and tell us what we're seeing in these images.
John, can we return to the previous slide? I have one more thing
yes, absolutely.
to add. Yeah, the deal is in the schedule for some projects, because clients, our customers, sometimes they want to have a fast prototype that can be made from off-the-shelf parts, for example. And in case of TIR lens using in this design, it means that it needs to be produced. It is almost impossible to choose some kind of TIR lens off the shelf that will be fully suitable for some projects with strict requirements like here. And this is one, perhaps, the most important reasons to use this assembly of the lenses that can be buy off the shelf.
So these are off the shelf elements that you're using, and that was done intentionally to speed up the delivery time.
In this design, these are custom lenses, but we plan it to move to the off-the-shelf lenses after the approval from the client side.
You start with custom lenses to figure out what you need, and then you can back into off-the-shelf lenses. Yeah. Okay.
Yes.
Okay. So what are we seeing here? I mean, what I'm noticing is, I guess the images are similar. So are these the same optical elements you have in these? They're a little bit different, maybe, but you have these 4 optical elements, 2 condensing and 2 imaging, and an aperture here. What else is happening in this screen?
We have 2 condenser lenses which collect the radiation from the LED. Then we have a rectangular aperture that stop or absorbs light that is not useful for us, that can form some kind of light flares. And also this rectangular aperture is the base for the illumination field form. After the rectangular aperture we have 2 lenses. We can say that this is some kind of projector optics, and these 2 lenses project plane of the rectangular aperture into the plane where we need the illumination field.
Okay. So now we're seeing the Zemax images, and these are uniformity images. Is that right? Tell us about what we're seeing here.
Yes. These images show how the light is. This is in irradiance of the radiation in the plane, and we see non-uniformity of this illumination field. Bright red is the bright part of image, and green and blue is areas with lower irradiance.
Got it. And then what is this big? What are these? Why have you made these systems with these boxes? What do these 2 other images mean?
So the second image shows the field of, no, this is not the field of view, this is an area that client wants to illuminate. This is white black image in the center, and on the right image I cut this area to show how the light is distributed relative to the area.
Because maybe in some applications, not only is it important to get uniformity in the target area, you don't want light in the other areas.
Yes.
And they were concerned about light in the other areas.
This was an idea, to show how what amount of light is out of the required area.
Okay. So now this says illumination for the outside of the working area. So this is explaining the same information, or what is?
This is the same information. We can see closer how the irradiance is distributed relative to the area of interest for the illumination system.
Got it. And each of these pixels is 1 millimeter. Is that right? Each of those little.
Yeah. Pixel size is 1 millimeter per 1 millimeter. So one small rectangle in the image of irradiance is 1 square millimeter.
Got it. Okay. And here.
The same thing.
Okay, so here now you're talking about what your next steps are. So what were your next steps?
So we showed the client how the system works, what type of field it produces, and of course the next step is to achieve required uniformity of the illumination area. And also we need to increase efficiency of the illumination system, so we need to achieve required level of the brightness of the irradiance, and we need to fill the required illumination area. Also there were requirements for the size and for the placement of the optical system, and we can try to make the system smaller, or we can add some kind of tilt mirror between lenses in the assembly. It also can help to place the optical system inside the required volume. And the last step is to search for off-the-shelf lenses then can be placed into the assembly and provide results that can satisfy the client.
Got it. So looking at this, these two images here. So I don't know that we did the optimization or we needed to, but just looking at this, if you were trying to increase the uniformity, what tricks would you use? What would you look at different for? Would that be something that you'd do? You'd update the condenser lens or the imaging lens, or add in diffusers. What ideas would you consider for the increase of
there are two stages of optimization. The first step is to have the most uniform illumination in the rectangular aperture plane, because this rectangular aperture is projected into the area of the illumination, into the illumination field. But we need to take into account that we have a huge distortion, and if you will show the slide where placement of the illumination system relative to the area of interest, here is it. You can see that the illumination system is placed at the angle, not perpendicular to the illumination area, and this burns some distortion, and we need to take into account this distortion. And this means that we have the second step, how to optimize the projection part of the illumination system. These are two lenses after the rectangular stop, and I can say that for this shown concept, this is impossible. In the final design, we add some optical elements that were placed not symmetrically to this optical assembly. We used some non-centered additional apertures, and we used cylindrical lens that also was placed not symmetrically to the optical axis of this assembly. And as a result, we corrected distortion a bit, good enough we make it good enough to satisfy the client. We achieved a good efficiency and good uniformity in the illumination area. Additionally, we decreased area of the illuminated area outside the required area.
Okay, great. Well, thank you, Sergey, for giving us insight on your work and talking us through this IR projection, IR illuminator program. I'm always interested to learn about the work that you do as an optical engineer. Thank you again, and we'll see you next time.
Thank you, John.
Okay, thanks, Sergey. Bye-bye.